Okay. What you can do is you can pack a bunch of double slits side by side and create something called a diffraction grating. And you see these in spectrometers, okay? You see these in spectrometers, you see them on telescopes, you can even see them on microscopes, depending on what they're trying to look at. What a diffraction grating does is it takes that central maximum and makes it narrower and taller. So it makes it sharper. It makes a brighter, sharper central maximum, and it sort of pushes down the other maximum. So say on a spectrometer, what it does is since the spacings are wavelength dependent, it will spread out the spacing of the different colors so that I can look at individual spectral lines. Like I can look at individual colors. Okay, so diffraction gratings are basically bunches and bunches of double slits packed together. And so it's like a double slit, but the spacing then is the way you find it is you take the number per centimeter. Like capital N will be, it'll say it's 1,000 per centimeter or 1,000 per inch or something like that. So if it's 1,000 slits per centimeter, then the spacing between each one is 1/1000th of a centimeter. So you just do 1/n to find the spacing. Again, it's like a whole bunch of point sources. So it's a whole bunch of in-phase light that then you basically do a bunch of double slit calculations on. And the more slits I have, the stronger my pattern becomes. So ideally, you want as many slits as you can get for what your money can buy, basically. So like a research grade telescope might have 50,000 per centimeter. All right. And it also makes the lines narrower, more like it keeps them from spreading out so much so we can pinpoint exact numbers of wavelengths and so forth. So this is an example of what this diffraction grating does. So the picture here, you can see the central maximum is still all the colors combined. But then what I'm interested in is like the first order, where the blue and the red are split up. And that's what I want to see are the individual colors. And then in the second order, you'll get them split even more. So it allows me to take, say, white light or starlight or light off of a flame test and split that up into the individual colors. Okay, so single slits work in a similar way, except there we have the opening is wider. And so what happens is the wavefront acts like an extended point source. And so the wavefront itself is the source of different sections of the wave. And we're only going to talk about this from the perspective of discussing it. We're not going to solve any problems with it. But with a single slit, we're more interested in how wide is that central maximum, because that's what's going to give us our image. And remember when I talked about resolution, I talked about those central maximums overlapping. So what I'm talking about with a single slit is how wide or narrow is that central maximum. So what I'm really looking for there is the first dark spots, because that's what's going to define the width of that central bright spot. I'm looking for the dark lines on either side. So there we're looking for destructive interference instead of constructive. The analysis works in a similar way, but for a single slit, what you get is much stronger, wider central maxima. And so like your eye works like a single slit in some cases, or an aperture on a telescope or a microscope. You can have a circular aperture where your central maximum, instead of being a line, is a circle. This is called the airy disk. And so when you're looking at something in a microscope or a telescope or with your eye, if the wavelength is such that you get diffraction, what you would really like is for this central thing to be the brightest and these other ones not to be so bright, so that you can make out a sharp image. And this is what we're worried about overlapping when we talk about resolution. Now, the other thing that we can talk about when we talk about constructive and destructive interference is a phenomenon called interferometry. And interferometry is used in a lot of different applications. It makes holograms. It's a way to do failure analysis and so forth. So what we do there is again, it's about path length difference, okay? So we have one beam of light coming out of like a laser. And we use what's called a beam splitter. So it's a half silvered mirror. So part of the light goes straight through, part of the light hits the mirror and bounces up this way. Now, those two arms are dialed in to be a certain distance apart. Maybe they're dialed in to be exactly the same length, so the light travels exactly the same distance. And so if it's in phase when it leaves the beam splitter, it's in phase when it gets back to the detector. Okay? How an interferometer works is one of these arms is fixed and one of them is movable. So if something causes one of the, or actually they're both movable in some cases, but in either case, if something causes one of the arms to move and change that path length, what will happen is while it's moving, you'll see the pattern of fringes move on the screen because it'll go from being constructive to destructive to constructive to destructive, depending on how much this changes in length. So what happens is it builds an interference pattern on the screen. This is how we detected gravity waves. The LIGO detectors are two big arms that are basically 4 kilometers long, okay? All right. And the gravity waves, when they come by, you know, they've sat there for 15 years waiting on something to happen, and that interference pattern doesn't move. When the gravity wave comes by, it squishes space-time going one way. So basically it shortened this arm, and that interference pattern moved, and scientists lost their minds, which was awesome. But that's what we do. We change the path length. We can do this using mirrors. Or if you're going to make a hologram, what you do is the path length difference happens because you're diffusely reflecting the laser beam off of something that has dimension. So I've got the same thing. I've got a beam splitter. Part of the light ray goes straight to the photographic plate. Part of it goes over and hits my object, in this case a cube. The front of the cube, the light travels a different distance than the back of the cube, or the top of the cube, or the side of the cube. So what happens is all that light that's diffusely reflected off that cube, when it gets to the photographic plate, it's in, when it gets to the photographic plate, it's in different phase than the, light from the reference beam. So it creates an interference pattern on that film. Now here's the key. When you look at a hologram, it just kind of looks like a blurry fingerprint. What it is it's the fingerprint of that light, because to be able to see that image, if I shine the same wavelength of light on that photographic plate, it will interact with that constructive and destructive interference pattern to give me the reconstructed image of whatever it was that I was taking a picture of. Okay. You want to be part of class? Okay. So you got to be on a video, so now you're famous. All right. So when I look, then it's a virtual image, okay, because the light doesn't actually go through there, but my eye looks through that hologram and it sees the image of whatever it was I was trying to reconstruct. So where can I use this? Astronomy, we use it all the time. We use it for connecting big telescopes together to make them act like larger telescopes. We use it in a series of, when we're trying to look at diffraction patterns. In seismology, you can use it to see if fault lines are moving. So you have detectors with laser beams on them from, like, on, say, fault lines, or they use these on, like, lava domes. For example, Mount Rainier has one on its lava dome to see if it's moving. Mount St. Helens is the same way. They could to see if the lava dome is growing and by how much. Metrology, when you're looking at failure analysis in materials to try to see if a beam is bending or swaying, or if a building is moving without actually having to destroy the beam to see. And then obviously, you know, a lot of before we started having the chip in our cards, we had holograms, and then they use it in, you know, entertainment industry now too. So, and data storage, it's a really good way to store data because, you know, you break up with your ex and you try to cut them out of a picture. That works great for a visible light picture, but you can't cut them out of a hologram, because a hologram, all the information is stored on every part of the hologram because of the wavelength of light. So you can't cut them out. So you know. All right. Okay, so that is all the stuff that I had for you guys today. Um, so before I stop the recording, I just wanted to remind you guys, so whoever's listening to this that's not in the class today, if you have questions or if you need something, email me, or we can chat on here, or we can email back and forth, whatever works. But if you know of anybody that's having trouble with connectivity or having issues getting the class materials, please let me know so that we can accommodate them somehow, because I want everybody to be able to finish this class successfully. Okay. All right. Does anybody have any questions about anything? No? Okay, well then I'm done for today.